All right. Hello, everyone. I am Professor Dill, and yesterday we did like the first section of this Python programming textbook, and I did find like an interesting paper that I really found interesting, and I thought we could just go over it. I'll kind of tell you what parts I think are really neat. It's only 13 pages. So if we get through it and we still have a little bit of time left, maybe we can go into the other textbook as well. So I found this paper on JStage, which is a Japanese journal. So it's talking about concepts for adjustable artificial intelligence. So I feel like there is several ways of talking about the same thing. So sometimes you might run into this word, artificial, general intelligence. And then other times you might run into something like transfer, deep learning. Okay, and then here, this paper, they're kind of they're suggesting an adjustable AI. So I feel like all of these terms kind of mean the same thing. Basically, it's trying to make an AI that is general enough that the actual architecture itself does not really get changed. Um, you're just applying it to different tasks. In this example, it's video games. They are proposing a model that's just good at general, like a model that can play any game. And it shows how it uses it to predict strategies instead of specific actions. It's a little different. So let's get into it. Let's see what sticks out. Uh, So a lot of AI is specific purpose, like detecting handwritten text or determining if a picture contains a cat or a dog. So you see their thesis is to design an artificial intelligence adjustable to every type of problem without any modification to its source code. So basically they want to make like some kind of like just some kind of where you just have the game be the input and it solves the game. Okay, so AI is a significant part of computer science applications. Like I said in the last video, the kind of area between traditional programming and the new, let's say like the new age programming with AI, it's philosophically different, but then it merges at some point. Like for example, large language models, those you're kind of telling it what to do step by step, but then it's designed off of like a lot of examples, so it's kind of like a neat middle path. So AI is widely used in video games and robotics. So AI is good at is solving decision-making problems. So I've I know the Fast AI textbook, they said AI is it can predict, but it can't do actions. If you want to do actions, you have to integrate AI into like a larger program. So agents are entities controlled by the computer, can interact with the environment. So current AIs or traditional AIs cannot be used for multiple tasks. So let's say slash adaptable AI. I feel like all of these kind of mean the same thing. The idea with transfer deep learning is you take a pre-trained model and you get it to do something that it wasn't originally designed for. It's kind of like the same concept. So let's see, useful for generic problem solving. I, as far as like philosophy goes, I can tell that the author is viewing AI as a tool and with probably no potential to become like an independent artificial life form. I personally favor that view. Um, I feel like it's kind of naive, just and maybe even unethical to view AI as just a tool. Um, but it's hard to find people that agree with me, so take that for what it's worth. So they want an adaptable AI to win every kind of games. So this reminds me of like the first few episodes or lectures in this playlist. The author of the first textbook we tried, he said AI, a big part of AI is defining the rules of the game, or maybe not. Maybe the trend is not to define rules, just give examples. Like again, the field's really still early. Like even though it's been like going on for 50 years, compared to physics, physics has been going on for 2,000 years. So, and in contrast, AI is really, in the grand scheme of things, it's pretty open field. There's a lot to discover. So, the first layer finds a global strategy. Second layer converts strategy into a sequence of actions used by an agent. So, what might this look like in real life? That might look like having a script that uses like xdo tools on Linux to perform keyboard and mouse movements. So the third layer can override the second layer in order to handle emergency cases. Okay. I feel like they could get rid of this third layer, but let's see what they arrive at. So the first section shows basic knowledge of AI. Okay, so this section discusses about some basic knowledge. So I did find this visualization useful. So they talk about game states. A lot of this paper is stuff I've tried to put into words before in previous lectures. They do it a little bit more elegantly. They call it game states, where it's the AI is constantly checking the game state, and if there's any anomalies, then it suggests different actions or whatever. Um, So there's two kinds of AI. There's like your NPCs, or you have AI that either plays the game entirely by itself or it assists a human player. So if you want like some street terms, this would be like one might call it botting, another might call it cheating, where you're like using AI to enhance gameplay. I think that's the most interesting part is using AI to interface with computers better. I think that's really powerful. Like for example, Neuralink, it wouldn't be possible without like machine learning, decoding the uh, neurons firing statistics within the brain. So then when you have like NPCs or like predator missiles or for shooting game, maybe not. So we have like scripts, that's like your X2 tools or AutoHotkey or PyAuto GUI, Pinput. These are all like keyboard and mouse libraries. So you see the actions, the agent can move, can perform actions in the game. This is kind of in contrast to what the first textbook. I didn't like the first textbook, but it basically said like, or actually the Fast AI textbook. It said AI can only predict, which is kind of naive because this paper is suggesting that AI can be embodied in an agent or whatever, and it can perform actions. So I like this definition. It's like why not? If it can predict, why not just integrate that into something that can do actions as well? So they break down a game into a system. System has all the data representing the game state. So they divide it into environment and the agent. So they're taking like they're they're forcing like a Western ontology into their model design. For example, our environment would be like the Linux desktop environment, X11 or Wayland, and then you have like your display servers as well, which might be like GNOME or XFCE or Cinnamon. So I found this paragraph particularly useful. So during each iteration of this cycle, the system sends a complete or it's just part of the game. It sends some information of the game's current state to the agent. So we could say a loop is like 100 milliseconds. So let's say every 100 milliseconds, it's checking the screen to get the game state. Okay, I'm looking. It's so every 100 milliseconds, the game state is getting updated. Um, that might be you might need faster loop or a slower loop depending on the game. Like a real-time strategy, you might be able to get away with 10-second loops. um, on this topic, I know AlphaGo or AlphaStar, when they worked with Blizzard, I know from the documentary, Blizzard, one of the reasons that they that one step of making that happen was Blizzard providing the Google DeepMind team with a version of StarCraft where it's like it's like a very bare bones version of the game where the time can be shrunk. So like a typical StarCraft game takes maybe half hour to an hour. So if you like played it back at a million times a second, then you can iterate many games very quickly, and you can learn way quickly. When you break a game down into like just basic formal logic or just like raw, like I'm thinking of it like Arc Linux, where Arc Linux is like it's like the binary version of like if Microsoft, if Windows is like the Python language of computing, then I think I lost it. Um, Lost the analogy. Okay, so AI is part of the software controlling the agent's behavior. AI receives the current game state. So these are keywords. When you're looking at a paper, you want to find like the words for tension. That might be like however or but. These mean like the author is taking a stand. He might be going against the grain or the common understanding of a field. So this is a keyword for tension. So he's saying creating an AI, adjustable AI, applies that whatever the game's objective, environment, or player, the AI would lead the game, lead the agent to victory. So an AI that can work in any environment is what they're looking for. So he's saying there's two ways. There's a knowledge-free AI, full extracting the game's characteristics. So that might be like something without any a priori knowledge of the game or the environment. So this is typical of multicolored tree search. He says this is not ideal because it requires long-term playing. So I think the author is leaning towards this other way, which is to make AI which learns by itself the characteristics of the game it is playing on. So this is proposed by this paper 7. Maybe we should read that down the road. It uses a neuroevolution algorithm. So this one has a flaw. So intended gameplay is kind of alien. So it seems like it's kind of too alien to understand, maybe. Or they don't exploit the things they learn, maybe. So this is the solution the author is offering. This is the value of the paper, I would probably guess. So they want an AI that searches for a strategy instead of actions. So that's the key. That's the key word. So they want an AI searches for strategy instead of actions. Now, this it's kind of vague because wouldn't a strategy imply actions? Maybe there's like a technical reason the author worded it this specific way. So they're using the MC algorithm. So they're combining two algorithms to achieve this. So what's the problem with this method? The problem is to combine the use of strategy within the context of an adjustable AI. Studies propose to group action sequences together as suggested in 9. Our solution is another way to represent the concept of strategy and generate them. Our work is parts of the second type of AI, which improves by learning the game's characteristics. It has for ambition to be usable on every type of game. So think of like one AI model that can play AlphaStar, play Go. It can solve the protein folding problem. If the game like it the game the word game is also very vague because you can formulate anything to be a game. You know, life you could say life's a game of prolonging death, for example. So it's very ambitious. This is a very ambitious paper. So they want to use a multi-layered AI able to discover and manage the strategies corresponding to the game. So the strategy game will continuously improve. So, all right, so framework design. Framework design, the global design of the program. How many models compose AI and all different their purpose and the ways they interact together. So it's a 3-layer framework. Each layer has several modules. Sub-objects and elementary actions. So every video game is based on interaction between the agent and the virtual environment. So video games, in this case, it's kind of like a sandbox environment. It's like walking before you can run. Because the next step, obviously, after you solve this issue, like if they do solve this problem of making an AI that can play any video game, it may be like better than a human is like a longer term goal, but if they achieve this, and the next step is obviously to go outside the games and apply the model to solve games out in the real world. So games can be broken down into a set of actions. To the games, these actions affect the game. So we call them elementary actions. So break games down into elementary actions. All right. Sorry, my light. It's kind of annoying. Um, okay, so we have this graph. So the goal of the game is to kill a monster. you have these three possible elementary actions. You could drink a potion before doing some elementary actions. So you see which of these is better. Obviously, possibly B is better because not only would you want the monster dead, but you want your life to be max. You want a min. It's like a min max problem. But it might also be the optimal strategy to do A because maybe some effect on the magic agent's magic level or whatever allows you to beat the game quicker or perform better. It's sometimes having lower sometimes it's not simply a min max game that's very simple. Sometimes you have to sacrifice life to get more resources. So it's talking about RPG games where their agent wants to do things in order to progress. So the first layer, strategy layer, purpose of the first layer is to determine AI's global strategy. So this is real-time strategy, first-person shooter. So RPG, maybe you're not. Maybe the goal of the game isn't to do anything. Maybe it's like a collect. Like maybe you want to like collect all the items. You know, that's different than a real RTS and first-person shooter. Maybe yeah. So that'd be like MMORPG. So sometimes the meaning of the game is different and unclear. So they identify the goal is every type of victory. So the AI needs to know all types of victory. So what is that? So it's a pattern. If we know how, if we have a model that can detect patterns in cats, can we have a model that detects patterns and identifies what's a victory? Pattern recognition model that recognizes a variety of types of victories. So that's kind of an interesting concept, thinking about like different, not just different ways to win, but what kind of perspectives are there in winning, you know? Like games might define winning differently, so you need an AI that can tell what the developer intended is winning. A deeper question is like, if there is a god, then could an AI be extrapolated from this video game model that the paper proposes, and could a model kind of predict what the most likely victory state looks like in the real world? That may, if there was a designer or creator, that's what they intended, or is everything just relative? Um, So the first layer finds the best strategy. And then it sends it to the second layer. For reason of clarity, the strategies described in the figure are shorter than the ones our AI would generate. I think one flaw with this paper is it doesn't address like the game itself. So like if you're having a model, if you're training a model on a game, the model is restricted by the temporality of the game. Um, if you could compress the game to where like instead of being able to run 5 meters per second in the game, maybe in a jailbroken version you can run 5,000 meters per second. Then you would be able to play through the game and learn faster by because it's a video game. You can change time. Like developers have complete control over the physics of a game. So um, off the shelf games might be hard to manipulate. Even like okay, even one way around even like if uh you could train if you really just want to hack the problem, you can train the model on gameplay footage sped up 10x, etc. Okay, that's one way to hack it. Or you could just alter the game's temporal physics. So I think that's one thing this paper is lacking. So situation agent monsters, this is like the environment. Kill monster, buy health potion. These are two paths. Both these paths result in experience. But the problem with this, or not the problem with this, but like one of the things that this points out is, yeah, yes, it's important to get experience, to increase experience, but you have to have a grand strategy. You can't just look at the current environment and the current sub objectives. I think is that the word he uses, sub objectives. The AI can't just get narrow tunnel visioned on sub objectives. It has to have a grand strategy, and that grand strategy should be able to um, determine which of these paths is better. So this is really the difference between like narrow AI and um, a more sophisticated AI. So list sub objectives related to RPG. Okay, so these are the sub objectives. So one objective might be like uh, collect all the items in the game. Might not. That might involve killing monsters, but it might also involve doing like other things within the game that's kind of outside the norm. So improving on existing strategies is an important aspect of their model. Okay, so I get the point here. So first layer grand strategy identifier. Okay, and then second layer is optimized action sequencer. Choices of what and how are separated. Okay, so it should be able to update itself, because there is like random contingencies that can happen, so it should be able to update. This is why it's not really practical for like us like for an individual. I feel like it's not practical for an individual unless you're like really you have a lot of money, because to compute this in real time at like 100 milliseconds, imagine running like an A100 on a cloud, and also the latency. Like I know running the cloud, it's you can do the compute on the cloud, but then there's like the latency issue. An A100 in my room is going to perform better than an A100 to 200 kilometers away. That's just basic physics. There's a time delay. In that few milliseconds of delay of light traveling 200 kilometers might be enough to affect a performance in fail a sub objective. So that's why cloud computing at some point is not a solution. Or yeah, cloud GPU latency may be a problem for real-time updating models on game states. All right, so how are we doing on time? Got 20 minutes left. Okay. Okay, so this is where the third layer comes in. The third layer is kind of like a good friend that tells you when you're being crazy. The third layer is like a support system that just takes a different perspective, maybe prioritizes like safety, or just it's specialized situational awareness. Um, Emergency detection. Again, like I said earlier, I think this could just be deleted. I think that might just be clutter. Um, yeah, I think I would just disagree with the third layer. I think you only need two layers: grant strategy, and sequence optimizer. Um, an emergency responder should just be like in the first layer. It should just be in like the first and second layer should just be talking to each other. Like, is this action aligned with the grand strategy? Uh, oh, something random just happened. This is messed up my optimized sequence. Check the grand strategy. Communicate with another. Can we compute another optimized strategy in this new environment? It should just be like automatic. I don't think a third layer is necessary. I get why they see it as important, but I think it's just clutter. So let's say for example every 100 milliseconds, the AI receives a complete copy of the game state. So like I said, when we ask a model on the Google Cloud GPUs to determine if this is a cat, it takes a few seconds. Um, few seconds is a very lot longer than 100 milliseconds. So that's how we can say cloud GPU latency may be a problem for real-time updating models on game states. Start data represents the game state. So, like I said, the game state can be altered. Like if you have a customized version of a video game that's different from the commercial on the shelf version, and that's better because then you can alter the physics of the game. You can loop things faster. You can if it takes an hour, let's say it takes 10 hours to speed run one video game. If you have a custom version of the video game, it could take 100 seconds to speed run the game because um, you don't have to process the graphics. Um, graphics are necessary for the human playing the game, but an agent can just break the game down into formal logic and action sequences and just a set of actions. Um, but maybe the graphics are necessary for determining the victory state, like what type of victory it is. Maybe the graphics are necessary for that. But then even that you could just instead of transferring 60 frames or 120 frames per second, you could just do like 1 frame per minute, and you might be able to get the same result. So yeah, so how I would change this would probably just be like have layer one go into layer two, have layer two go back into layer one, and then maybe then you go to the action. I don't know. Okay, so I'm just wondering if the author addresses the GPU latency issue. Maybe it's just not a concern. It might just be like theoretical. But if you're actually implementing this, you need to like consider like the actual engineering problems. So they this is a famous one, the physical traveler salesman problem. All right, RTS, that's like maybe StarCraft. Yeah, so they do reference StarCraft. Oh well, they actually have a screenshot of the StarCraft one. You should, if you haven't, you should watch like the highlights of this game, because the way it moves several units at once is like very alien, very cool, very inspiring. So RTS, real time RTS. So RTS is a management of resource collected, and yeah, just using your various resources wisely, because there's like a time element to RTS. So if you don't act, yeah, I mean, I guess there's a time element to everything. Yeah, so it has to react quickly. Author still is not talking about GPUs at all. Concern. So game state can be broken down into object IDs, a type of object, and a number. Objects data character. So I wonder how much this, because there is a term object oriented programming that's like Python's an object oriented programming language. So is that how like games are? Is that like the framework that games are made off of? I wonder. So so some information is not, so the game's not just its objects. It's a important point. A so raw information, or is this some not expressed as objects? Thus, inference is required the neural network takes as input the game state and the strategy to evaluate. It outputs the strategy's quality. It doesn't say how, like, it doesn't talk about any, like, keyboard or mouse scripting languages, or it doesn't talk about how they're going to implement this model into something that does the actions. It just kind of, this is very theoretical, and it doesn't have any, like, doesn't go into, like, the practicalities, like GPU latency um, or how to do the actions, how to actually perform, how to make the model do the actions. So I'm surprised he hasn't mentioned GPUs once. That's and the author hasn't really. The author has kind of given like narrow examples, but he hasn't really discussed how like any use cases where like a general adaptable AI has like worked at all. Maybe he's referencing something like that here. So superhuman AI is able to detect those sub-objectives. What is what is the neat method? Okay, so neat. Okay, so here's another key. Neuro evolution of augmenting topology algorithm. So I think we should read 7. 7 seems like a really good paper. Okay. Volume 9, issue 2. Oh, that's not what I want. It's kind of weird that I can't even find the paper that they're referencing. Is it this? John Lehman? Okay. I think it's this. Okay, so they use this AI to play Atari games. So does it reference GPUs? Does not reference GPUs. Well, actions. Reference actions was so it does reference actions a lot. Doesn't say how. Maybe the source code is this. Okay, so man, this is 13 years ago. This is a fork of this. Hyper neat. 2008. Okay, so we're out of time. It's like I don't really know how to read. Oh, here we go. What is this? Hypercube based. So this website talks about HyperNeat. Maybe I'll put this in the description. I don't know if anyone even would use this these days. Field moves pretty fast. It seems pretty cool though. So it hasn't been updated in like 5 years. So why did this die? You know, what happened? So maybe I'll bookmark this. maybe we'll come back to it. I'll post this paper and the other one in the references. So yeah, I'll end it there. Thank you guys for hanging out, and I'll see you next time.